This section is about some kinds of differential equations which are called separable, which you can solve. You cannot solve all kinds of differential equations, but separable differential equations is one type that you are going to be able to solve. So solving a differential equation means that you found an equation that satisfies that differential equation. So when you take the derivative of your solution, you get the differential equation. There are two types of solutions. One is the general solution, which would involve a plus c, and the other is a particular solution, which you can only find if you have an initial condition, so then you can figure out what the plus c is. So here's an example of a general solution problem. The general solution is the entire family of equations that are solutions to the differential equation, and it includes a plus c. One way you can think about this is that the opposite of a derivative is an integral, so you can just go backwards and find the antiderivative. A more formal solution to this differential equation would be to say, I would like to take the integral of both sides of this equation. However, I can't do an integral without a dx. So to solve that problem, like an integral sign by itself is not an operator. It needs to have a dy or a dx with it. So in order to solve the problem of not being able to take a derivative, what we do is we're going to multiply both sides of this equation by dx. So then we have dy is equal to tangent of 3x secant of 3x dx. And now when we throw an integral sign on there, both of those integrals on both sides of the equal sign are attached to a differential. So each integral has the full operator. This side of the differential equation would become y plus some constant, but we're only going to have a constant on the other side. And this side needs a u substitution in order to fully solve it. So we could say u equals 3x, du equals 3 dx, dx equals 1/3 du. So then the antiderivative would be 1/3 secant of 3x, and then we're going to need to have a plus c. This is a general solution, because if we take a derivative of this, we get this dy dx. And the general solution will have a constant in it because the constant goes away when we take the derivative. Sometimes separable differential equations are a little bit more complicated. This looks like a differential equation that came about because of implicit differentiation. And so in order to undo this, what we have to do is move the x's and the dx's to one side of the equal side and move the y's and the dy's to the other side. So let's go ahead and do that. I'm going to square out first. So this would be x squared y squared is equal to dy over dx. And then in order to move everything around, I'm going to multiply by dx. And I'm also going to divide by y squared. So I wind up with y to the negative 2 dy is equal to x squared dx. Now that everything is separated out, we can take the antiderivative or integral of both sides, remembering that there'll be a plus c, but we're only going to put a plus c on one side of our equal sign. So this would be y to the negative 1 divided by negative 1, and this would be x to the third divided by 3 plus c. Really, we would have a constant on both sides of the equal sign when we do the antiderivative, but the constants wouldn't be the same. And then we'd take the constant from the left side and subtract it over to the right, and we wind up with a new constant. We have to have a constant, but it doesn't have to be like the same constant as it was before. It's okay that it's a different constant. The constant is sort of arbitrary. There is a constant, we don't know what it was. And then our last step, we're not done until we get this thing solved for y. So we're going to solve this for y. We're going to divide by -1. So we get y to the -1 is equal to negative x cubed over 3 plus a constant. And notice how I didn't say minus a constant, because this constant is the opposite of this constant. Again, it doesn't matter what the constant is, there just has to be a constant. So that's kind of a new wrinkle, is that I'm not really that particular about what the exact c was. This is a c, a constant, is going to be added on. And then I'm going to take both things to the -1 power. So I get y is equal to 1 over negative x cubed over 3 plus c. Or if you're bothered by fractions on top of fractions, you could multiply both sides of this by 3 over 3. So y is equal to 3 over c minus x cubed. And I'm going to emphasize again, this c is 3 times bigger than that c, but they're both constants. So that's cool. All right, that is the solution to this differential equation. The solution for a differential equation is going to be the one that is both a solution to the differential equation and satisfies some initial condition. You can't find a specific solution unless you're given an initial condition. So here's our initial condition. Our differential equation is dy dx equals 3x squared. So we're going to multiply both sides by dx. And then we'll do the integral of both sides, and we get y plus some constant is equal to x cubed plus a different constant, but then we can move the constant over. So now it's x cubed plus some arbitrary constant. And then we're going to plug in our initial conditions. So we have -3 is equal to -1 cubed, which is still -1, plus c. So c would be -2. And it's really tempting to circle that as your solution, but your solution is the equation, remember? So your solution would be y equals x cubed minus 2. This constant is no longer an arbitrary constant. It's an actual value based on our initial condition. So when you have a separable differential equation that actually needs to be separated out, we're going to do the same process. We're going to move the dy dx's over to the same side of the equal sign. We'll take the antiderivative. And then you can solve for c or you can solve for y first. It doesn't matter which one you do first, but you do eventually have to solve for both. Your solution needs to look like a y equals equation, and it must have the value for c in place. So I'm going to multiply both sides by y, and I'm going to also multiply both sides by dx. So times y and times dx for both sides of this equation. So this would be y dy is equal to -x dx. And I really want to emphasize that I'm keeping the y side as simple as I can, and the x side, that negative sign, I decided to leave it with the x side because I will eventually solve for y, so I would like the y side to be as simple as possible. So this would be y squared over 2 is equal to -x squared over 2 plus some arbitrary constant. I'm going to go ahead and multiply both sides of this equation by 2 at this point. So I have y squared is equal to some arbitrary constant minus x squared. And I'm emphasizing that this c and this c are not the same. The second c is twice as large as the first c, but I don't really care what this c is. I eventually just want a constant filled into my equation. All right, I'm going to choose to solve for y first. So I'll do that. So I have y is equal to plus or minus the square root of c minus x squared. Remember, when you solve a squared, you get plus or minus. But when we have a solution, we want it to be a function. And right now, this is not a function. The way we're going to decide whether to use the positive version or the negative version is we look at our initial condition. Okay, so our initial condition says that y is -3, which means we will be using only the negative version of y. So we have -3 is equal to negative square root of c minus 16. I'm going to square both sides. So I get 9 is equal to c minus 16. And then I'm going to add 16. So c is equal to 25. Which again, that's not my solution. My solution is y is equal to negative square root of 25 minus x squared. And the reason we're only using the negative version again is because we would like our answer to be a function. And if it's plus or minus, it wouldn't pass the vertical line test. Here's another example. I would encourage you to try this and pause the video and then restart after you have tried it. Pause now. Pause, try it, write it down. So I hope you were able to get your dx's and dy's over to one side of the equal sign and then do the antiderivative of both sides. Now we both need to solve for y and we also need to solve for c. I'm going to start by solving for y. I think that's easier. It's not always easier, but I think it is in this case. So I'm going to take both sides e to get rid of natural log. So e to the natural log of the absolute value of y is going to be e to the x squared plus c, and the plus c is in the exponent. On the left-hand side, e to the natural log is going to, they're inverses, so they wind up with just absolute value of y. And on the right side, I have e to the x squared times e to the c because of this property of exponents. A to the b times a to the c is equal to a to the b plus c. So I just broke that addition in my exponent down into a multiplication with the same base. I'm going to emphasize again, e to the c is a constant. I don't care what the constant c is, I care what the constant e to the c is. I care what constant I have in the end. But so I'm going to call it P just because this is so different. It's not 2 times C or anything. I'm just going to call it P. So then I have the absolute value of y is equal to P times e to the x squared. And I know e to the x squared is positive, but I'm not sure about P. So I'm going to say y is equal to plus or minus P times e to the x squared. Now I'm going to use my initial condition. Since my initial condition is negative, I will be using the negative version of my equation. So I have y is equal to negative p times e to the 0 squared. And so negative 3 is equal to negative p, which means p is equal to 3. So our equation is going to be y is equal to negative 3 e to the x squared. All right. So these are separable differential equations. You are going to be solving both for y and for the constant that makes the differential equation true for your initial condition.